Hello guys, in this video we are going to see exercise 1.5, 1.1 in your textbook, right? So the first question is like, use Euclid's division algorithm to find the HCF of 135 and 225. Let's solve the first question first. So to apply Euclid's division algorithm, the first step is to apply Euclid's lemma to the given numbers. Euclid's lemma is A is equal to BQ plus R, where 0 less than or equal to R less than B. Okay, here I am applying Euclid's lemma to 135 and 225. I'll do the division over here. 135, only one time it will go. 135, the remainder would be 0. 12 minus 3 would be 9. So the remainder is not equal to 0. So we can write 225 in the form of 135 divisor into quotient 1 plus remainder. Since the remainder is not equal to 0, again apply Euclid's lemma to the remainder and the previous divisor, which is 135. Again it will go only one time, 90. If you subtract 5, 13 minus 9 would be 4. So 135, the second step is 135 can be written as 90 into 1 plus the remainder 45. Again the remainder is not 0. Again apply the algorithm. 45, the previous divisor is 90. 45 to 90. Yay, the remainder is 0. So the previous divisor 45 will be the HCF. The last step in the algorithm would be 90 is equal to 45 into 2 plus 0. The last divisor 45 will be the HCF. HCF is equal to 45. So the HCF of 135 and 225 is 45. So to perform the second one, I'll remove this one. Okay, let's remove this. Just give me a minute. Oh my god, why? So the second question is 196 and 38220. It looks like a big problem, but yeah, let's solve this. So the first step is apply Euclid's lemma to 196 and 3880. 196, 38220. I think 196 one time only will go. 2 times it will be more than 382. So you subtract 12 minus 6, 6. And here 7 will be there. 17 minus 9 would be 8. 2 minus 1 would be 1. I'll take 2 here. 1862. I think 196 nines it will go. 6 nines 54. 9 nines 81 plus 1. So it will be 6 here. 9. 9 plus 9 17. So 19 nines are 1764. Obviously 196 into 10 will be 1960. It will be more than this number. So here if you subtract 0, 6 minus 6 also. Sorry. This is 4, no. This is 4. 12 minus 4 would be 8. 6 minus 6, 0. Sorry. Here 5 will be there, no. 15 minus 6 would be 9. Here 7, 7, 0. Then take 0 here. 196, 980. I think 196, 5 should go. Let's see. 30, 5 nines, 5 nines 45, 48, 5, 6, 7, 8, 9, 980. Yes, 5s are 9. Oh, it exactly divided the number. This is only step 1. Step 1 is 38220 is equal to 196 into coefficient is 195 plus remainder is 0. In the first step itself we got 0. So the divisor 196 is the HCF of the given two numbers. Therefore, the HCF is equal to 196. Okay, that's it. I think you can solve this problem. No, 2 I have solved for you. Third question is your homework. Please do that question and comment down the answer below. Okay, we'll see the next question. Show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus y, where q is some integer. So we need to show that any positive integer is in the three forms, in the given three forms only. Here we have solved the examples which are in the form of 3q plus 1. No, in similarly we will solve this also. So the first step would be, let a be any positive integer, and here I can see it is in the form of bq plus 1, bq plus 3, bq plus 5. So I'll take my b as 6. Okay. Then by Euclid's lemma, you know that if any given numbers a, b, you can write a is equal to bq plus r, where 0 less than or equal to r less than b. So here also you have the condition on r, right? If you write our a as a is equal to b, here is 6q plus r would be, take r only, where 0 less than or equal to r less than, here b is 6, so 6. So what are all the possible values of r? R can be 0, 1, 2, 3, 4 and 5. These many possible values of r. That's right. So if r is equal to, our a will be in the form of 6q plus 0, it will be 6q only, no? If r is equal to 1, a is in the form of 6q plus 1. If r is equal to 2, a is 6q plus 2. If r is equal to 3, a is equal to 6q plus 3. If r is 4, a is equal to 6q plus 4. If r is equal to 5, a is equal to 6q plus 5. We need to show that any positive odd integer is in the form of 6q plus 1, 6q plus 3 and 6q plus y. So here if you take 2 in common, you can write it as 2 into 3q. It is in the form of 2 into something which will become even. So, and second one, it is in the form of 6q plus 1. I'll write it as 2 into 3q plus 1. Since this is even plus 1 will be always an odd number. So this will become odd. So if a is in the form of 6q plus 1, it will be an odd integer. Again, a is equal to 6q plus 2. This I will write it as 2 into 3q plus 1. This is also 2 into something which will always be an even number. Then this one I'll write it as 2 into 3q plus 1 plus 1. 2 into something plus 1, which will always be an odd number. This I will write it as 2. I'll take in common 2 into 3q plus 2. 2 into something I have written. 2 into something is always even. This one 2 into, I'll write it as 3q plus 2 plus 1. 3 to 6q plus 4 plus 1, 5. Right? 6q plus 5. This will be an odd number. 2 into something plus 1, which is always an odd number. So where we got odd integers, 6q plus 1, 6q plus 3 and 6q plus 5. That's what they have asked us to prove, no? Show that any positive odd integer is in the form of 6q plus 1, 6q plus 3 and 6q plus y. Hence proved, right? Then next question. An army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. What is the maximum number of columns in which they can march? So there's this army contingent of 616 members and 32 members. So this 616 members has to march behind this 32 members. Okay. So if you arrange 32 numbers in 2 columns, 616 members also you should arrange in 2 columns only, one by one, one by one, one by one. Like that, if you arrange, what is the maximum number of columns in which they can march like this? Suppose if you are arranging 32 members in 32 different columns, 616 members also, you should be able to arrange in 32 different columns. Okay, so like that, what is the maximum number they are asking? Simple. HCF of 32 and 616. Let's find 32, 616. Euclid's lemma. Apply it. 32 ones 32. And if you subtract 9 over here, 5 minus 3, 2. 6 here. 32, how many times it will go? I am thinking 9 times. 9 to 18. 9 3 is 27, 28. Yeah, 9 times. If you take 288. If you subtract 6 plus 2, 8. So the first step would be 616 is equal to 32 into 19 plus the remainder is 8. Since the remainder is not equal to 0, apply HCF to the remainder and previous divisor, which is 32. 8 1s, 8 2s, 8 3s, 8 4s are 32, no? 8 4s are 32. So the remainder is 0. The previous divisor is 8. So the final step would be 32 is equal to 8 into 4 plus 0. Since the remainder is 0, the previous divisor 8 is the HCF of the given numbers. Therefore, HCF equal to 8. Therefore, the maximum number of columns in which they can march is 8. Okay. Then next question. Use Euclid's division lemma to show that square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Again, same procedure. Let a be any positive integer. Positive integer. And here I can see bm plus 1. So I will take my b as 3. Okay. Then by Euclid's lemma, a is equal to bq plus r and 0 less than or equal to r less than b. Here, since b is equal to 3, the condition would be 0 less than or equal to r less than 3. So what are all the possible values of r? R can be 0, 1 and 2. Okay. So if r is equal to 0, a will be in the form of 3q plus 0 will be, it's the same thing, 3q or 3q plus 0. Then if r is equal to 1, a will be in the form of 3q plus 1. If r is equal to 2, a will be in the form of 3q plus 2. Okay. Here they are asking the square of any positive integer. So squaring on both sides. A square is equal to 3q whole square, right? I will divide it like this, just to, okay. Then a square I can write it as 9q square. A square I can write it as, if I take 3 in common, 3q square. It's known that q is any integer, right? So 3q square will be another integer, let's say m. Then a square is in the form of 3m. Okay. Here also squaring on both sides. Then a square is equal to 3q plus 1 whole square. A square is equal to a plus b whole square formula. A plus b whole square is equal to a square plus 2ab plus b square. We know this, right? I hope you guys know this, you remember this. So a square is equal to 3q whole square, which is 9q square, plus 2 into 3q into 1 would be 6q, plus 1 square is 1. So I'll write a square as a square is equal to, if I take 3 in common, here and here, I will get 3q square plus 2q plus 1. As we know, q is an integer, so the entire thing 3q square plus 2q, let's take m. Then a square is equal to 3m plus 1. Okay. Now let's do this. Squaring on both sides. A square is equal to 3q plus 2 whole square. Then a square is equal to 3q whole square will be 9q square plus 2 into 3q into 2. 3 to 6q into 2, 12q plus 2 2s are 4. This here also I'll take 3 in common. Then here you will have 3q square plus 12q. In 12q you have 4q. Here see, 4 I can write it as 3 plus 1, no? So 1, 3 here I'll take common 1 plus left out 1. Again q square plus 4q plus 1, take m. Since it is an integer, a square is equal to 3m plus 1. So what are all the forms we got? A square equal to 3m, a square equal to 3m plus 1, a square equal to 3m plus 1. That's what they've asked us to show, no? You use Euclid's division lemma to show that square of any positive integer is either of the form 3m or 3m plus 1. 3m or 3m plus 1. Hence proved. Next question. Use Euclid's division lemma to show that the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. First step, let a be any positive integer, and b here, see here we are not going to take b as 9, because if we take b as 9, our remainder, the possibilities for our remainder would be 0, 1, 2, 3 and so on till 8. You have 9 possibilities for the remainder and it will be very lengthy to solve this. So we can consider here b equal to 3 for the two reasons that, of course, 9 can be written as 3 into 3, and since it will become lengthy, let's consider b equal to 3. All the things that which are applied for 9 that are also applied for 3. So there's no harm in taking b is equal to 3. Then our remainder possibilities is 0, 0, 1 and 2, since 0 less than or equal to r less than b. Okay. So then a is equal to, a will be in the form of b cube. b is 3 and q. And if r is 0, a equal to 3 cube. A is equal to 3 cube plus 1. If r is equal to 1, a is equal to 3 cube plus 2 if r is equal to 3. Now cubing on both sides. If you cubing on both sides, a cube is equal to 3 cube whole cube. A cube is equal to 3 3 is 9 and 3 is 27 q cube. Then a cube is equal to, you can write it as 9 into 9 3 is 27 q cube. Since q is an integer, you can write this as m3 cube as an m, which is another integer. So a cube is equal to 9m. Okay, that's it here. Now cubing on both sides here, a cube is equal to 3 cube plus 1 whole cube. We need to know this formula. A plus b whole cube. I hope you know this formula. A cube plus 3a square b plus 3ab square plus b cube. This is the formula. Let's apply over here. A cube is equal to 3q whole cube plus 3 into a square is 3q whole square into b is 1 plus 3 into 3q into 1 whole square plus 1 cube. Let's divide this. Then a cube is equal to 3 3 is 9, 9 3 is 27 q cube plus 27q square plus 9q plus 1. Here if you take 9 in common, 9q cube plus 9q square plus q plus 1. Again, q is any integer, no? So the entire thing will become another integer. Let's say m. then it will become 9m plus 1. Our a cube is in the form of 9m plus 1. Now consider this form, a is equal to 3q plus 2. Now again cubing on both sides. A cube is equal to 3q plus 2 whole cube, which we can write it as a cube, which is 3q whole cube, plus 3 into a square, 3q whole square, into b, which is 2, again 3 into 3q into 2 square plus 2 cube, right? Here again you can write it as 9 cube plus 27 cube plus 27. It's not 27 over here. 27 into 2, which is 54 q square, plus 3 is 9. Again 9 into 4, 4 9s 36 q plus 2 8. Here if I take 9 in common, 3q cube plus 6q square plus 4q plus 8. If this is m, an integer, let's take this as an m as an integer. A cube is equal to 9m plus 8. It is in the form of 9m plus 8, either 9m plus 1 or a cube is equal to 9m. It can be in only in these three forms. A cube can be 9m or 9m plus 1 or 9m plus 8. That's what they have asked us to prove. No, use Euclid's division lemma to show cube of any positive integer is of the form 9m, 9m plus 1 and 9m plus 8. Therefore proved. That's it for this video. So with this we have completed exercise 1.1. We'll see you in next video. Until then, bye bye.